I welcome Dr. Aviv Mezer from ELSC, and I'll just say a few words on Aviv. Aviv received his PhD at Tel Aviv University in biochemistry and neurobiology. He then worked in Yaniv Asaf lab in Tel Aviv University before he left to do his postdoc at Professor Brian Wandel's lab at Stanford University. In his postdoc, he was working on quantitative MRI, qMRI, methods such as relaxometry and diffusion imaging to measure biophysical properties of the human brain tissue. Aviv uses these new methods for mapping the brain development and aging processes, as well as structure-function relation in cognitive processes such as reading, and for diagnostic of the brain disorders such as multiple sclerosis. Aviv joined ELSC this month, and we wish him success in establishing his new lab. So good luck. And today Aviv is going to talk about accuracy and reliability of quantitative and diffusion MRI models. So thank you, Aviv.
Thank you for the introduction. And it's a pleasure to be here and feel at home. I'm going to talk about, so Yaniv actually did a great introduction, also introduction for the problem that I want to talk about. There was this word of belief, and we have to believe, and maybe we can try to evaluate the model and establish when we should believe a model or not. So I'm going to talk a bit about that, mostly highlight work coming from others at Wandel's lab where I did my postdoc, and toward the end I will speak a bit about how we can add other imaging tools to add to diffusion and increase our understanding of the biophysics. Okay. So with diffusion, we saw already we can talk about connectivity, how different brain regions connect. We can also try to talk about microstructure, define big fiber tracks. We can try to speak about microstructure, about the specific properties of cellular organization at the tissue, and also to relate it to function or clinical application, which I'm not going to talk about at all today. Okay. So we saw before diffusion is sensitive to the orientation of cellular microstructure, and the diffusion properties will be different if diffusion is measured along a pathway versus in perpendicular to it. And so we raised this question more than once in the talk. How can we validate that the model that we use then to feed the data is valid? And especially, how can we do it in vivo? Because there was this idea of maybe validating it ex vivo with postmortem work, but can we do something with the data that we have and try to evaluate the model that we use? And so here again, another just nice image. So let's look at the signal again, and it's going to be a movie. Maybe you're going to look at here. This is the corpus callosum. Right now it's dark, but as I'm swiping the direction of measurement, we're getting different images. Maybe we can do it again. And sometimes it's bright, and sometimes it's dark, depend of the orientation of the direction of the gradient that we use versus the orientation of the fibers that we try to image. And we can look at then on this measurement, on this image, and this is 3D shape, and there is areas in this direction which is very low signal, and there is high signal in the other direction, and that's the source of information that we then use for the modeling. And so we saw already this equation in which you have the measured signal, we have the baseline signal, the S0. We have the diffusivity, if we believe this model of the Gaussian distribution of diffusion. And then we have the B value, which we also already talked about, and we noted that it's a function of a gradient strength, gradient duration, etc. And so we can measure, let's say, the signal in the same location here in the corpus callosum in different B values. And the first thing you might notice is that the signal change. The signal change in terms of amplitude, and the underlying tissue is the same. So what happens is that our SNR drops. As we increase the B value from B value of 1,000, which is a typical clinical, and also most of research actually use, we have pretty high signal. And as we go down with B values, which will be used then for more sophisticated model, the SNR drops. On the other hand, we have much more information when we go to higher B values, and we saw it before from Yaniv. We're getting to have the sensitivity to differentiate between underlying microstructure. There's also higher angular resolution, which I'm not going to talk about at all in higher B values. So there is a value in higher B values, but then there is also a drop in signal. Okay. And so we measure, and then we can we can fit a model. Yaniv was elaborating about the tensor model, which described the diffusion by this 3D cigar shape. We can also do something else which called spherical harmonic deconvolution, which you can think about it as a way to have more than one tensor shape P of the signal. And these many more models. I will talk about this model, which is multiple tensors that are combined together to fit the data. And then the question is, how would we know that it's a good idea to do that, to change a model? And so one idea, which that will allow us to do it in an in vivo way, is to take a data, scan it once, and maybe we're going to scan the same subject again, or maybe we're going to save some of our data. And then we can first ask what is the reliability between data to itself, right? So we can do test-retest reliability just to check to see what is the noise in our measurement. How reliable is this signal? And then the other option is to take this data, fit a model, and then having this model, we can try to predict the other data, right? So this prediction this thought is actually very simple. People in engineering and in statistics know it. It's called cross-validation. Some have been forgotten in diffusion, but it's a good idea, right? We can fit the data, have a model, and try to predict another data set, and then have a way to establish if our model is good or not, is correct or not. And so if we take one observation, we take one observation, one diffusion set, and then another one, we can plot them one against the other, and you can see there is a little bit of noise, right? We can estimate the noise in the data. And then the other option is to take this data, fit a model, and then try to predict this data by the model. And this is with TTM in diffusion tensor model. And one thing you might immediately see is that actually diffusion tensor is doing quite well, in the sense that it's better than the reliability data to data is worse than the reliability of data to model. So the model actually captures most of the feature in the data and reduce the noise in it. And so and I would suggest that this idea of modeling another data set is a good way to establish if our model is a good model. Okay. So we can also formulate it with some kind of metric that is the relative root mean square error. In this metric, we can ask what is the root mean square between model on one data to predict another data, plus the vice versa compared to data to data. And whenever this ratio is below 1, we can say that the model is better than our model is predicting the data better than just repeat the measurement twice. Okay. So we can check now. I will change the b values and check this relative root mean square error, and we said that if it's below 1, it's good. And so in low b value, just fitting a tensor, you can see the white matter in particular is green. That means that we hear a lot that tensor model is bad. It's bad in many ways, but it actually fits the data pretty well. And then there is this question: you want to infer more and more about the tissue, but it might be that the model that we're using is actually quite sufficient to the data we have. So in low b value, I would argue that the tensor model is actually a pretty good and well-behaved model. As we increase the b value, you can see that these regions that start to become whiter, and if I really increase the b value to this very high b value that Yaniv was using before, then there are regions when the model is totally wrong. So two things. One, we can look on those regions in a second, but the other thing is that the tensor model is not such a bad model in terms of fitting the data. Not in terms of predicting the underlying biophysics, but in terms of fitting the data. And if we want to ask what is going on in here, this is the issue of crossing fiber, if you remember. So in this spot, it's actually a known region where we have we have the callosal fibers, and we have the SLF here, and the cortical spinal tract, and they all meet around this region. And then we have just many tensors. There's more than one feature of, that we try to fit with one tensor. And let's say we can predict one fiber with a tensor, and we can maybe create a model for another fiber with a tensor. When we try to fit them both, we get this pancake-shaped thing, which is not such a good model of the data. Another problem of it is also that it doesn't capture the right orientation, right? It gets some kind of like in-between orientation, which I'm not getting into at all in here. Okay, so another models or other models, which is still, I don't know where you would fit in between the parametric and non-parametric. It's just the idea of we're going to add more and more tensors. And then the problem with adding more and more tensor with different orientation, and then also the isotropic component, is that just we have many parameters. So when you have many parameters, they obviously will fit the data better, but there will be an issue of overfitting. And then there is method to try so many try to find ways to minimize this problem and try to not to overfit. Using different regularization approaches, which I'm not going to get at all in here. We use here a sparse minimization. We try to find the minimal set that can fit the data. And so in here we have not only the isotropic part of the signal, and then many tensors. If this math just looks bad, just remember the other image. We have a ball and few tensors that might have different orientation. And now we can ask if that's better predict the data. And the answer is yes. So in the low B value, it was already green. We don't do much better. But as we increase the B value, we still stay in this nice region of having a pretty good prediction of the data with this multiple tensor model. Okay, and if we want to evaluate it in general, you can see that in low B value we have some improvement, but it's not dramatic. And as we increase the B value, there is more dramatic improvement in terms of predicting the data when we use more complex model. So all of that is not for really to argue for this model. It's just for give you the feeling that we have ways to evaluate models. And when you have a problem and you have data, you can try to check different models and see which one is the one that will fit your need best and fit your data best. So these two issues, which are not always the same, your need and your data. Okay, so to conclude this idea is that first, model in diffusion predict the data pretty well, and then the tensor model doing a relatively good job. It gives us these values, which I will talk more about later, which have at least some kind of infer something about the biophysics, and that using more complex model, we can like this one, we can actually have even better models, which will predict the data better, but we have to test it with our data. So again, with low B value, it's probably there is no reason to go to these more complicated models, because probably there won't be any value, which your reviewers might not agree, by the way, because there is also trends in those things. Okay, next, how would we evaluate tractography? So in tractography, we try to connect, right, fiber to create this connection between regions in the brain using the diffusion data. And if we zoom into this region and we look on this small tensor that Yaniv showed us before, and now we use our favorite tractography algorithm to connect the dots and try to find the fiber. And as you might heard, there's many flavors of tractography algorithm. Each of them has its own set of priors and initialization and assumptions, and that will change the route that we're going to get. So for instance, okay, this is the pathway that we want to get, and there is many models. I actually want to highlight this one. I'm not going to speak much, but Amir was asking before about using some kind of structure specific and then compare everything in there. this AFQ tool, which is all in MATLAB and all open source, will allow you to do all the analysis on the subject space. I think also Michal will use it next. Yes, she will. Okay, so now two different algorithms. One was probabilistic, and the other one was deterministic. Again, that's different parameters that will define how we characterize the pathways. And here we're looking on the aggregate fasciculus, and you see a totally different pathway. I mean, it has kind of the same shape, and one is really bushy, and the other one is really clean and tight. And so what is true? It's actually getting worse, of course, because then you have the cortical spinal tract, which is just nearby it. And again, one is more bushy than the other. In this region, we also have now crossing fiber. In this model, we have no crossing fiber. Who is right? And so, and then last, also where they eat the cortex. One will eat the cortex really in a greater regions temporally and parietally. The other one have really specific region when it's hit the cortex. Which one is right? I mean, the typical hand wave thing to say will be that probabilistic is probably have many false positive, and deterministic probably have many false negative. And then what do you prefer? More like what kind of uncertainty do you prefer? But that shouldn't be the way we would go. We can try to evaluate that. So okay, so just summary the differences. And then Franco, which was at Brian Lab but now is in Indiana, was suggesting this new algorithm called LIFE. And the idea in LIFE is that we're going to take these pathways and we're going to go back and try to predict the signal again and see which one is actually working. And so we will reject the pathway that doesn't explain the data, and we will accept track that actually help us predicting the data. And it all will be done with this linear formalization of the problem. And so the idea here is now we have the data. We typically go and predict a pathway from it. We create using the tectography algorithm to create a track. Now we can go in the other direction and say, okay, if this track has some kind of diffusion properties, how good is it predicting the data? So again, I'm not arguing from one algorithm to the other. Actually, it's still an open question, and there's many open questions of how you do it correctly. But I want to advocate the idea that we can go and evaluate the goodness of the tectography algorithm and check which predict the data well. And yes.
So it has nothing to do with the model. It's only based on the attenuation of the signal.
Say it again. So
based only on the signal attenuation of the raw data.
So you want to predict the signal attenuation, given that there is some model that there is model. Okay. It is model. There is a model in here in this linear ID. You give each fiber you give it a tensor essentially, which then you need to model this tensor, and then you would have maybe many tensors in each voxel, right? Now you get this crossing fiber ID again from the other side, and then you put a weight on each fiber in this in the linear equation that you solve, and you ask what is the weight for each fiber to predict the signal. So yes, there is still modeling. There's always assumption in all those things. You can play with that as well and ask yourself what is the correct model. They definitely use a tensor here. Okay. And then just to give you a flavor of what they found, in general at least, this is each dot here represents a voxel, and the axis here is a root mean square error. The probabilistic we're doing better in this case in terms of predicting the signal. Okay, say that it's bigger, and what this method allows us to do is first do things like a virtual lesion. We can take away a pathway and ask what happened to the signal now. Did we actually need this pathway that our algorithm find? Is it actually helping us in predicting the signal or not? So creating this kind of virtual lesion. We can add pathways. Let's say our tectography didn't work and didn't find, or maybe it worked, but it finds a set of pathways, and we think there is another. Let's say we force it. Does it add any value in terms of fitting the signal or not? So that gives us a way to test and try to reject at least the false positive tracks. Okay, and with that, I'm gonna move to the things I'm doing, and I'm also gonna do it short. So again, we saw we saw this image before. We're fitting a model to the data, and this tensor has also some feature which has biophysical features, which is useful. One of them is the mean diffusivity, which we don't see much, but believe me, there is an image here of a brain, and it has some units. And we also have the FA, which can vary according to the shape of the tensor that we fit, right? And this orientation, which I'm not going to get into, and we heard about. And so the original thought when people use this kind of data was when we have a very low FA, it's probably because the underlying tissue, this is EM image of axon in early development stage. There's something that in this case there is a lot of space, water diffuses more, and then FA will be lower. It's closer to a ball shape. While let's say in development or in a mature tissue, we'll see much more structure, much more organization, and then FA might be higher because there is just less space to move. And then this kind of view were used then to capture variation in FA and in diffusivity as function of age. And so in here we can see different pathways defined by tractography, and then each dot represents a subject, the average along for a subject. Y-axis is function anisotropy, and x-axis is age, and color is boys and girls. Not important for us here. And so this one is RFA, and this one is mean diffusivity. And you can see that there is we can explain some of the variation in the group as function of age. And there is a model that we can fit. There is typically a Poisson model in which there is much greater change in the early age, and then the decline is not as big in older age. Okay. The problem with this view was, and it still is, that as we already spoke, diffusion is not as well understood, or at least the tensor model doesn't capture the full feature that biology might underline, or the underlying biology. So there is many reasons why there will be change in diffusivity or in FA, and although the signal is very sensitive to them, we don't know exactly what was the source of the variation. And one big one is, of course, crossing fiber, which become is a rage now against those methods, saying that you can never use this model because there is always crossing, and you're never really sensitive to one pathway in the brain. Okay. And so what we did is to use other quantitative methods and try to see if we can add value and learn something more about white matter structure if you would have other methods. And Yaniv already told us a bit about that. So this is a T1 weighted image. That's the image that is weighting the T1. And it's actually, but again, we're typically using that and using for these different kinds of like visualization or VBM. This is actually physics that can explain this signal. It's a signal equation that we pretty much understand. And so we can try to evaluate the real biophysical sources for the signal. And so what we know is that if we vary one of these parameters, we can try to fit the proton density, or 1 minus proton density, which will be the macromolecule tissue volume, if you want the fraction of water to non-water in its location. And the other main source of the variation, as the name says, is T1. So we can also fit T1, and now we have a T1 map, and it has units of second. So one has units of second, the other one has units of volume. And there is some relation between them, which I'm not going to get into, but we now have at least two new dimensions of the data, and we can look on our white matter structure and try to say what was the real source of variation, let's say, that we saw in FA or in diffusivity and so on. Okay, so why it's so useful? Because let's say we use MTV, macromolecular tissue volume. If there is less tissue, it's just going to get us a very low MTV value. The interpretation is just more straightforward. If there is more tissue, MTV will be greater. And so it's just very, very, very basic thing. And it was hard to measure, but from the moment we have it, actually diffusion sounds like a bit complicated. That sounds very simple. The other one is R1, or 1 over T1, which was recently, again, we show this kind of interaction. More water, lower R1. And it was recently done by post-mortem work, and they were able to show that most of the variation in amount of myelin can be explained by about 90% of the variation in the white matter in the amount of myelin can be explained by R1. So it seems to be that R1 is a very, very sensitive measure of myelin, although it's not one-to-one. It's a very good predictor of the amount of myelin. Okay, and I'm going to focus on R1 for the next 3 slides, something. So we saw this one before. We saw the variation in diffusion as function of age. Now I'm showing you the variation of R1 as function of age. And so x-axis is age, y-axis is R1, and each dot is a subject. And you can see that and we then fit a model, which I will speak in a second. And you can see that each pathway has different variation as function of age. And so we can, of course, then make a nice image with color codes, which the bluish mean not so much variation in terms of R1 as function of age, and red mean a lot. And we can look then on those pathways and essentially color code them about according to the amount of change that we see as function of age. And you see that there is a big variation in that. Okay. But is it just the same as diffusion? Do we measure something new? We're just measuring diffusion. So what we found is that there is actually a very weak correlation in terms of both mean diffusivity versus mean R1 value per track. It's not a very good. They're not really a good predictor one of the other. Also true in the amount of change. The amount of change in R1 is not a really good predictor of the amount of change that we will measure in diffusion. And all of that is arguing that there is multiple biological sources that we are sensitive to with the different modalities that we measure. It's also true in the term of the model that we fit. What we find that R1 look like a parabola. The amount you gain is exactly the amount we lose in a function of age, at least in these ages, in this age range. And it wasn't true in terms of diffusion. In diffusion, there was much more increase in early age, and then is the decrease is not as big, although they both peak around the same age. And when we try to explain that, and that's hand wavy, but that's open for more modeling, what we think is happening is that both diffusion and R1 are sensitive to this developmental effect of increasing tissue complexity and myelinization. And so R1 goes up, diffusion goes down. But with aging, when axon dying and myelin is lost, R1 goes down, while the area that now is not occupied by axon is now filled with glia cells. And so the diffusion will still stay restricted. So we think that while R1 went back, diffusion didn't, and that's because there is there is still restriction effects from the glia cells that's still affecting the diffusion. And again, that should give you the feeling that using those two measurements and many more actually, we will be able in the future to try to build a model of the underlying tissue. Okay. And with that, I'm going to say thank you. It was too fast. Maybe it was too fast. Okay, that gives us time to question. I would say first thank you to the people who actually did this work at Brian Wendell Lab. It was Jason, Ariel, and Franco. And now all of them are not at Stanford anymore, in Seattle and Indiana. And we are now in a recruiting step. So if you're interested in this kind of work, you're welcome. And thank you for listening. Any questions? Or was it too fast?
What else besides the myelin, the
MTV reflects everything that is not water. So any kind of macromolecules that exist there will affect MTV. So PD, proton density, will be affected by just a fraction of water to non-water. So it could be proteins, lipids, membrane, anything. while R1 or T1 is affected by this, by the proton density, but also by the kind of macromolecules. So the fact that there is more sphingomyelin or less, more cholesterol or less, iron. So if you want the biophysical makeup also affecting T1. So it's actually interesting we're actually doing that. We try to model the signal having proton density or MTV and T1 and try to ask what can be explained just by the amount of tissue and what can be explained by the biophysical makeup of the tissue. So, yeah.
On your last point regarding glia cells and aging, which affect diffusion and not one can assume that R1 is a better measurement than diffusion. Are you suggesting that?
No. Well, better in what sense?
I don't know. Is it completing the diffusion?
I think it's completing it. Well,
used instead?
Well, it depends for what, right? For instance, I couldn't estimate where the fibers are without diffusion. I was using diffusion to define the pathways. I couldn't do that without diffusion because there is no orientation information in T1 mapping, for instance. In terms of specificity, I think the specificity of the T1 and proton density model is well better characterized. I wouldn't say that it's fully characterized. Also, there is still room for improvement, but it's better characterized than what you gain with, at least with the simple diffusion model, which is tensor model. When you go to more and more complicated models, in diffusion you get more and more specificity with the price of scanning longer, which people try to make it shorter, and with the price of overfitting, which is there is less work about that, but when you fit more and more complex model, there is a question if you're actually fitting data or noise. Please.
About this level study that you showed,
Mm-hmm.
also, I think in the study they show that in young age it's not just like the RG that goes down, like the radon diffusivity, also like the AD.
Yeah.
It's very related
Yep.
to water quality in the brain. I wonder if it affects the same like the
Right. So there was the question was, I just showed the mean diffusivity, but you can open a discussion about AD, which is or the AD or the radial diffusivity. So the different component of diffusivity. This was trendy, and then it stops. And the reason is that it's unclear that you can actually capture much more with that, and we're not really certain about the orientation anymore with tensor. So I feel safe to talk about mean diffusivity. I feel less comfortable to talk about the different components, although you can. Yeah.
How did you measure T1?
So T1 was, we were doing multiple flip angles. So looking at the equation, I will go back. I didn't say anything about how I'm doing that. And in here. So we use the multiple flip angle idea of that in theory, if you just vary the flip angle, then you can fit T1. The big problem is that we don't know what is the real flip angle. I mean, there is the nominal value that we get in the scanner, then there is the B1 inhomogeneity. And so a big part of the work was to essentially create a B1 mapping procedure which will be fast enough to run along this thing. And so to getting the true so there is problems with T1, for instance. It's very hard to measure it reliably and correctly, which we think we're doing very well now. So this for the benefit and disadvantage of diffusion versus T1. T1 is very early age now, and there's only few groups that actually are able to do it reliably. And so then the biggest reason is that we have these flip angles, and we say in the magnet we want like flip angle of 10 degrees, 18 degrees, and we're getting something. You're going to do it twice, and you get something else. And so the nominal values and the real values are not we're just getting scanners which are not calibrated. We should really yield on the companies, but they give us uncalibrated machines. And then there's also variation in space, which have to do with the interaction between the tissue and the gradient. And so we actually have to map B1 inhomogeneity. This is variation in alpha whenever you scan a subject. So that's another obstacle in getting a good, reliable T1.
Are there works on maybe animals that correlate the myonin binding protein to the R1 net that you showed?
In animals. So there is this the one that I am familiar with is this postmortem work, which they were actually then doing myelin staining, and show that this is highly correlated with myelin. Not that I know actually, and there is also work with biophysics that show that there's other sources beside myelin that affect R1. So I take it with a grain of salt. It's happened to be that it's really correlate with myelin. It doesn't mean that it's a myelin measure. Okay, thank you so much.